Every time you type a sentence to a language model, something quietly happens before the model thinks at all. Your words are turned into numbers, long lists of numbers that live in a space with hundreds of dimensions. This is the embedding layer, the doorway between human language and machine math. Let's open it up. A model never sees words the way we do. First, your text is chopped into pieces called tokens. A token can be a whole word, a piece of a word, or even a single character. The word embeddings might be split into embeddings. Then each token is looked up in the model's vocabulary, a fixed dictionary of every token it knows, and replaced with its ID number. So your sentence becomes a short list of integers, but an ID is only a name tag. The number 8738 tells the model nothing about meaning. It is just an address. So how do we turn an address into meaning? With a giant lookup table called the embedding matrix. Picture a wall of drawers, one drawer for every token in the vocabulary. A model might have 50,000 drawers. Each drawer holds not one number, but a whole list of numbers, its embedding vector. When a token ID arrives, the model simply opens that drawer and pulls out its vector. The entire job of the embedding layer is this lookup. And the contents of every drawer are learned during training, never handwritten. Let's look inside a single drawer. The vector is just a list of numbers. Here, 384 of them. Each number is a coordinate. Why 384? That is a design choice called the embedding dimension. Smaller models might use a few hundred. Large ones use thousands. More dimensions give the model more room to capture nuance at the cost of more memory and compute. Every token gets its own vector of this exact same length. But a list of numbers is hard to picture. Here is the key idea. A list of numbers is a point in space. 2 numbers, that's a point on a flat plane left to right and up to down. 3 numbers, a point in a room now with depth. The model uses 384 numbers, which means a point in a space with 384 directions. We can't draw that many axes, but the math works exactly the same. Each token is a single point floating in this high-dimensional space. Now the beautiful part, because these vectors are learned from billions of sentences, the model arranges them so that meaning becomes geometry. Tokens used in similar ways end up near each other. Cat, dog, and hamster drift into the same neighborhood. King, queen, and prince gather somewhere else. The whole vocabulary becomes a map of meaning, where distance means similarity. That is how the model knows cat and dog are related without anyone ever telling it. And it is not just clusters. Directions carry meaning too. In a well-trained space, the step from man to woman is almost the same step as from king to queen, so you can do arithmetic with meaning. Take king, subtract man, add woman, and you land right next to queen. To measure how related 2 tokens are, the model compares the angle between their vectors. A small angle means very similar. A wide angle means unrelated. But there is a problem. The lookup treats each token independently. It gives dog, bytes, and man their vectors, but it has no idea what order they came in. To the embedding layer alone, dog bites man and man bites dog look identical, the same 3 vectors in a bag, and yet the meaning is completely different. The model needs a way to know each token's position. The fix is positional embeddings. We create a second vector for each position. Position 0, position 1, position 2, each with its own unique signature. In the original transformer, these signatures are built from sine and cosine waves of different frequencies, giving every position a distinct fingerprint. Many modern models learn them instead. Then we simply add the position vector to the token vector, number by number. Now dog at position 1 and dog at position 3 are no longer identical. Each carries both its meaning and its place in the sentence. Add those 2 together and you finally have what the model actually consumes, 1 vector per token that encodes both what the token means and where it sits. This stack of vectors is the true input to the transformer. Everything that follows, the attention, all of those layers, operates on these numbers, never on your original text. So let's retrace the journey. Your text is split into tokens. Each token becomes an ID, just an address. That address opens a drawer in the embedding matrix and pulls out a learned vector, a point in a space of hundreds of dimensions where meaning lives as geometry. A positional vector is added so order survives, and that is the embedding layer, the quiet translator that turns language into the numbers a model can finally reason about.